Hello, this is Mr. Jensen. Welcome back. This is the first video in the series of 3 on work, power, and efficiency. Today we will be focusing in on work. We're going to figure out the definition and components of work, as well as make some calculations. Make sure you follow along with your Cornell notes. This is a lecture for the section. You will need to use this information and the notes to help you with lab and also an exam. So, to begin, what does work even look like? You might think you know what work is, but that may not always be true to the scientific definition. We have 3 examples here. First one, in the upper left, we have an Olympic weightlifter. He's a Russian. He's lifting a lot of weight over his head. The second example is here in the lower left-hand corner. It is a boy running down the hallways carrying books. And the third example is off to the right. It looks like a lady carrying up a laundry basket up the stairs. Now, if we want work, we need to have 2 things. We need to say yes to both of these things. First of all, we need to apply some kind of force. We can be carrying something, we can be pushing something, any kind of force. Second, we need to cause some kind of movement or go some kind of distance. So we need 2 things, force and movement. Now this first example, believe it or not, this gentleman is not doing any work. There is no work going on here. Now, is he applying a force? Yes, he is. He is lifting those weights straight up in there and holding them above his head. The next part is key to work, is causing a movement. Since he is stationary, holding the weights just in one place above his head, he is not doing work. He is only applying force, but he is not causing movement. He is not moving the weights a certain distance. So, is he doing work? No. He is not doing any work. Next example, the student running through the hallways with books. He is doing work. Yes, he is doing work. That's a big yes. Number 1, is he applying a force? Yes, he has a force to the books, carrying the books. Number 2, causing a movement. Yes, he is carrying these books down the hallway. So yes, this is a good example of someone performing work. Carrying books, moving it a distance. And the third example. This is a great example of work as well. As you can tell, this lady is applying a force to the laundry basket. She's carrying the basket, and she's also moving it up a flight of stairs, so she's causing movement or going a certain distance. So this third example, there is work going on here. So those are some examples. You can maybe relate work to your real life as well, but make sure we have both of these 2 things going on. Applying a force and causing a movement. Next, what is work? Remember, follow along with your Cornell notes. A nice formal definition of work is that work is a quantity, some number, that measures a force acting on an object over a distance. Work is a quantity that measures a force acting on an object over a distance. And point out force and distance, we need both of those things to have work. So they go along with each other. Work is a quantity that measures a force acting on an object over a distance. Now, up at the top here, can we measure work? Can we measure work? Is there a way to put numbers to it? And yes, there is. We can calculate this like most things in physics, and here's the equation right in the middle of the page. We have work. That equals the force times the distance. Work equals force times distance. Make it a little bit shorter. I might refer to it shorthand down below. W equals FD, force times distance. That is how we calculate work. That is how we quantify it. That's how we put numbers to it. Now, we have our equation at the top. Work equals force times distance. Let's go ahead and take a look at the units for force and distance and put them together to get units for work. So, as you can recall from our last unit, force is measured in something called a Newton, or newtons. So force is measured in newtons. A lot of times we abbreviate that with a big N. Next, distance. As you guys have known since the first day of school, first semester, distance is measured in meters. We write that with a lowercase m. So newtons and meters. Now, when we combine newtons and meters, we get something called a joule. No, not the shiny things from the earth, but this is the unit for work. Joules, J-O-U-L-E-S. We abbreviate it with an uppercase J. So work equals joules. So I can say, wow, today I did 100 joules of work today. Or 50 joules. That represents how many joules I use. That is our unit, similar to a unit of distance, which is meters, or force have units of newtons. Work has units of joules. Okay, let's go ahead and practice this real quick. So we have our equation. We have force equals, oh, let me go ahead, erase that real quick. We have work equals force times distance. So, just multiplication. Let's go ahead and do these two practice problems. So in the first row, I have force of 1 and a distance of 2. What is my work? So I set it up. W equals force is 1. Should keep my units. 1 newton times my distance, which is 2 meters. As you guys know, 1 times 2 is 2. My units for work, let's remember, joules. So let me write that in a row. 2 joules. So you just multiply them times each other. Let's do one more practice problem, but I'm feeling you've already got this mastered. So we have a force of 25, a distance of 3. So say we wanted to carry a rock 3 meters. How can we calculate the work? We write in W equals our force, which is 25. 25 units are newtons. So work equals 25 newtons times our distance. Our distance is 3 meters. And that will give us our work. 25 times 3, 75. 75 joules is our answer. We need joules. Answer is not complete without its units. So 25 times 3 is 75 joules. So as you can see, the second example, we have a lot more work than the first one. It's because our force was greater, and our distance was greater as well. Let's move on. Okay, story problem. You're going to get a lot of these, so let's practice them. But similar to the last one, you just have to find the information yourself. So a forklift moves 34 meters carrying a 1,023 Newton box across the warehouse floor. How much work is done by the forklift? So I always start off by writing my equation. Work equals force times distance. So my force, I have to find it myself. It's not as nice as that last table. My force is 1,023 newtons. My distance, it tells us right away, distance 34 meters. So we're always going to use our metrics. We're not going to get yards or feet or miles. We're going to get meters. So I found my two variables. I found my force, found my distance. Now I need to multiply them together. Let me type that in. 1,023 newtons times 34 newtons equals, big number, 34,000. Yes, that's a 4. 34,782. Most importantly, the units, joules. That's big work. That's a lot of work, but that's about right. 34,782 joules of work for a forklift to move a 1,023 Newton box across the floor. Next one, second example. How much work is done by a person who uses a force of 27.5 newtons to move a grocery buggy, well here we say grocery cart, to move it 12.3 meters. So, once again, I like to write out the equation right away. Work equals force times distance. So, let me find my variables. My force, 27.5 newtons. Times my distance, 12.3 meters. So you're going to get these story problems. They will contain all the information you need to solve these work problems. So, my force was 27.5 newtons. I have to multiply that times my distance, the distance the grocery cart went, 12.3. I get 338 338.25. What am I missing? My units, joules. Excellent. Now, you might get a case where you want a story problem, you want it to have, I guess, different layers. So say I have a guy first taking a package, a box, with a forklift, doing some work on it, and then also later that person is moving a grocery cart. Now, can I add these two things up? Can I add these two values up if I want to find out how much total work this person did in one day? And yes, I can. So if I want to see how much work a person did all day, I'd add up all their tasks. 34,782 plus 3, 38.25, and I would get a very large number, 35,000. 120.25. So if I want to figure out how much work you did all day, we do our individual calculations, and then we can add them up at the end. Now, we're almost done here. Relationships. Yes, relationships. What happens to work when I change the force? Well, when I increase the force, I increase the work. This means it is directly proportional. When they're best friends. When one goes up, the other goes up. When one goes down, the other goes down. So I can put the down arrow for force, down arrow for work. So they follow each other. They're best friends forever. Now same goes for work and distance. If I increase the distance I have to carry something, say I want to carry a box really far, I am increasing the work. And this kind of makes sense. If I told you carry a 50-pound weight, 100 yards instead of 10 yards, it would take more work to do that. And these are directly proportional as well. If one goes down, the other goes down as well. So they follow each other. They're best friends forever. So when force goes up, work goes up. When force goes down, work goes down. When distance goes up, work goes up. And when distance goes down, work goes down. You can use this equation to help you remember that, or you can just remember it on your own. Okay, last slide. Old stuff, new stuff. So we learned about force diagrams back a while ago. And I asked you guys to figure out if things are balanced or not. So let's take a look. On this particular diagram, we have a force pointing up, normal force, and force pointing down, gravity force. They have the same value, 20. So if I ask you, are the vertical forces balanced? You could say, yes, they are. Now, horizontal forces. I don't have a force pointing left, and I only have applied force to the right. So that means they are not balanced. It's like no one else was on the other side of the teeter-totter. So not balanced. So what is the overall force? And this is a review. Overall force would be 5 newtons to the right. I'll just draw an arrow to the right. So, this is one of those multi-layer questions. We're going to put everything together. So we have our force now, 5 newtons. Now here's our situation. Xavier, he moved a rock a distance of 10 meters. Using the overall force from the force diagram, this 5 newtons, and the distance, calculate work. So I start off, work equals force times the distance. So work equals my force, which I got from the force diagram, the unbalanced force, that is 5 newtons. I have to multiply that times my distance, 10 meters. And I get my work, and that is 5 times 10, which is 50. Need a label, my units, 50 joules. And that is my answer. That is it. Thank you for watching. Make sure you took good notes. I will see you on the next video.